Professor, this is Siklali from Group 6 as well.
Siklali from Group 6 is in the house.
Hi, Professor. This is Adriana Velasco from Group 4.
From Group 4. Adriana Velasco is in the house. How are we doing? Everybody in?
Hi, no, this is Mindy, Group 10.
Mindy is in the house.
Oscar Anguiano, Group 5.
Oscar, Group 5. Oscar is in the house.
Professor?
Yes.
Robin Penalonso, Group 4.
Group 4. Robin is in the house.
Thank you.
Everybody in? Everybody in? Can I close the door now?
Christiana Tello, Group 5.
5, who?
Christiana Tello.
Christiana? Is in the house. All right.
Kimberly Lara, Group 10.
Kimberly Laura from Group 10. Kimberly is in the house.
Professor Tokwe?
Yes.
This is Sherelle DeLone from Group 8.
Group 8. Group 8. Sherelle DeLone is in the house.
Yes.
Hi, this is Devin, Group 5.
Devin, Group 5. Devin is in the house. Devin Martinez. Okay. Is the door? Should I close the door now? Who's coming in?
Jose from Group 7 is having problems logging in.
Jose from
Group 7.
What is Jose there?
He's texting our group chat. He's trying to log in right now.
Oh, okay. When he get in, let me know.
Okay.
Me.
You in? Jose,
Yeah.
You in? All right.
Yeah.
All right. Okay, so we...
Professor?
Yeah?
This is Estela. Sorry, I just got here.
Okay, Stella, good number?
Group 4.
Group 4. Estella is in the house.
Professor, this is Rebecca from Group 6. I just got
Rebecca from Group 6 is in the house. Becky is in the house.
We're all in the house.
Who?
Oh no, I said we're all in the house.
Ah, in the house. Time to shut the door. Let's shut the door. All right, we're almost there. Let's celebrate, everybody. Celebrate. We're almost there.
Get an egg.
We're almost there. After this chapter, one more chapter. All right, so today we're going to talk about solutions. Solutions are so important.
Professor?
Yeah?
I have a question really quick before we start.
Okay.
As far as like our homework in the summaries, will all of those grades be entered for Canvas like at the end of the class?
No. I'm gonna have those. I'm not putting those in the Canvas. No.
Yeah. Okay, so our grade won't get updated until after the class is over?
Yeah.
Okay.
Okay. All right. So chapter 13, solution.
Professor,
Mm-hmm.
you do attendance?
Yes, I did.
Group 4, Ashley Gutierrez, I'm here.
Group 4.
Professor?
Yes. And anybody else? That's it? Okay, let's start the lecture. All right. So we have solutions. Solutions that some that you deal with every single day. There's not a day that you don't have solution to problems, solution to solutions.
Professor?
Yeah.
Let me see. Someone is actually sending a message. I believe Joseph. Yeah, Jason Joseph Calderon.
Jason?
Jason Joseph Calderon. He's trying to get on, but he's in group 3.
So if you get in, let me know.
Okay.
Christy Gutierrez Angel. Group 3.
Christian Gutierrez is in.
Professor, can you hear me?
Professor, this is
Hello.
Yeah.
This is Tamisha from Group 2. Tamisha Pete.
Tamisha Pete from Group 2 is in the house now. All right. Anybody else?
This is Jason Calderon. I'm in, Professor, for from Group 3.
Jason.
Yeah, thank you.
From Group 3. All right, Jason. Jason is in the house. Anybody else before we start talking?
Can you please verify that you got me, Christy Gutierrez, Group 3?
Group 3? Yeah, I got you.
Thank you.
All right. So again, we said solutions as something that we do every single day in different areas of life. So we're going to talk about solutions today in relation to the study of material, the study of matter. How can we make solution out of matter? Matter is the study of what? Occupying space, having weight. Chemistry deal with matter. So now, how can matter be involved into solutions? All right, so here we go. A solution definition is a homogeneous mixture. Anytime you hear that word homogeneous, then you know there is no division. No division. Everything just uniform. It's a uniform system. You can't, there's no division there. All right? So like in each group, your group is a solution. It's uniform. You all work together. All right? Outside of your group, it's not. So we see a solution is a mixture. Mixture meaning well, we can separate that stuff. Even though it's homogeneous, we can still separate it. We talk about the fact that if we took some salt, put the salt in the water, stir it up, we don't see, there's no division. We don't see the salt by itself and see the water unless there's more salt, you keep adding more salt and the volume cannot hold that salt anymore. That's different. But once you have a homogeneous system, that salt is in our water. If you walk into the room, you see a glass sitting there, clear. If they don't tell you that that's salt there, you're never going to know. But we can separate that salt from that water because it is a mixture. There's no tie in terms of bonding, bonds, so therefore, no covalent bonding, nothing of that sort, so we can separate. No anti-bonding, we can separate. So we see we can boil the water down, evaporate the water, and then we have our salt. All right, we can calculate it. We can calculate the concentration of the salt after we know. Let's say we had a 100 milliliter of salt solution. All right, that's the volume. And we evaporate that water out of there, and we weigh the salt. We can do a mass percent of the salt in that solution. We can do a molarity of that solution. So the concentration can be expressed in mass percent or molarity. A solution is composed of a solute. So the composition, solute dissolved in a solvent. What is more is a solvent. What is less is a solute. All right? So the solvent is used to dissolve the solute. Solution exists in all three physical states that we've been talking about. Matter, according to this text, The matter we study here, the three steps we study here will be gases, liquids, and solids. These are three steps we study. We're not studying plasma, which is the biggest, the three states in relation to our study here. But we can fit solution into the three states. That are very important. So after this course, you can make all kinds of solutions and and sell them, make money. You can make gaseous solution and sell it. You can make liquid solution, sell that. Solid solution, sell that. So that's what you're taking this course for. Not for you to take this book and put it on the shelf. Go back to your solution and say, I'm going to make me a gaseous solution. I'm going to make me a liquid solution. I'm going to make me a solid solution. All right, let's make gas. We can take some gas.
Is this how you make mouthwash?
Yeah, I make mouthwash, yeah.
Okay, cool.
All right. So we see the gas, we can take, one gas can be a solvent, one gas can be a solute. The gas that is less will be the solute, the gas that is more will be the solvent. Gas. So that's air. Take for instance, air is a mixture of what? Nitrogen, oxygen, argon gases. All right? So that's gas. All right? Gas solution. So air is a solution that is made out of nitrogen and all that stuff. So liquid, we can have, the solute can be liquid and the solvent can be a gas. So that means the gas is more than the liquid, so that we have humid air. The air is humid. Water vapor in the air. That is one solution they never even thought about before. We say humidity. Oh, it's too humid here. Oh, it's too humid. I'm not going to the East Coast, it's too humid. So therefore, why? Why is that? Because there is a solution there. That solution is humidity, humid. Okay, humid air. So that means what? The solute is liquid and the gas, the solvent is a gas. That's humid air. So that's how you make gas solutions. All right, we'll come to the liquid solutions. Gas is, when the gas is a solute and the liquid, now we flip this around now, flip. So now this time gas is a solute and solvent is liquid. Soda, hey, soda drinks. Stay off that soda. Stay off that soda, student. Stop drinking soda. Stay off it. I've been watching you. All right. So how do we make the soda? We take carbon dioxide and pump that carbon dioxide in the water. And we make that. So therefore, the water is the liquid and its solvent is more than the carbon dioxide. So that's why when you open the soda, what happens? That's the carbon dioxide rushing out. Glad to go. Glad to run away from you. And so now we have, when the solute is the liquid and the solvent is also a liquid, meaning one liquid is less than the other liquid. Vinegar. Vinegar, which is the last experiment you're going to do today, not actually. Well, I mean, it's an acid-based reaction. But it could be, but we do even HCl anyway. So we already did that already. So vinegar is made out of acetic acid in water. Acetic acid in water. So that's what make vinegar sour tasting, because acid is sour tasting. So now if the solute is a solid and the solvent is a liquid, we just talked about sodium chloride not too long ago. Take some salt, put it in water. We have a solution of salt water. So now here's what you could do. When this class is over, go to the Pacific Ocean, get you some water sample for different parts of the ocean side. Collect that water, So sample number 1, sample number 2, sample number 3, and 5. Collect 5 samples, okay, from the Pacific Ocean. Now, you want to weigh the volume of each of those things. Put the volume down, and then you go out and then evaporate each of them. When you evaporate each of them, the salt you get out, you weigh the salt. You weigh the salt, and you can calculate the molarity of the salt from the Pacific Ocean. You can calculate the mass percent. So when you do that after this course, send me an email and tell me what you got for mass percent and molarity. Don't forget that. Make sure you write that down. I'll be expecting to hear from you after this course. All right.
Wait, Professor, can you repeat the step one more time?
Okay. So you're gonna go to the Pacific Ocean, right?
Yeah.
Just walk it down the line. Collect one sample here. Walk down. Collect another sample. Walk down. Collect sample of ocean water, right? Now, measure the volume first. How much of that volume? Maybe 10 milliliter, 5, 20 milliliter, whatever it is. Measure that first. You have that. So get yourself a notebook. You know, when you're doing an experiment like that, you will, make sure you record the data. So once you have the volume, then you go to evaporate each of those. Evaporate each of those. For that, on sample number 1, how much salt you got? You will have to weigh the salt. How much salt you got from sample number 1? How much salt you got from sample number 2? How much salt you got from 3, 4, and 5? Okay? You have that information. So now, whatever the volume was, you take the mass of that sample number 1 and express it over the volume. You're doing sodium chloride. So you weigh the molar mass for the sodium chloride is about 58. All right. So then you find out what's the molarity. Now, the volume, weigh the volume also. Weigh the volume before you do the evaporation. You got a volume, you weigh the volume, so you know how much the solution weigh, the weight of the solution. So the salt you got from sample 1, express it over the volume, the weight of the volume, multiply that by 100, you got a mass percent. Is that clear so far?
Yes.
Who didn't get it? Who didn't get it? You didn't get it? Okay. All right. So, solid solutions. We come to solid solution. When the solid is a liquid and the solvent is solid, that means you got more solid compared to the liquid. We have dental filling. Some of you are going to go to dental hygiene program. And so dental filling. So the mercury in silver. Amalgam. We had amalgam, mercury amalgam. Okay, that's the amalgamation. Solid, when the solid is a solute, and another solid is a solvent. Sterling silver, we passed it already. We saw sterling silver, copper in silver. All right. So you see how you can make money out of making solution? Some people already. Some company making sterling silver. You see, some company dental fillings making money out of this. There's a lot of money being made in this area. All right, so that you got to learn how to make solutions. Okay, people will buy that from you. Okay, so now temperature affects the solubility of gases. What role does temperature play in order for it to dissolve gases in solution? How soluble it is. Temperature plays that role. The higher the temperature is, the lower the solubility of a gas, because the gas is trying to take up. Gases, they bump around. When in a high temperature area, they can't stay, they gotta go. An example is carbon dioxide in soda. All right, go back to what your soda, those of you that drink soda, carbon dioxide. less carbon dioxide escapes when you open a cold soda. Okay, pay attention to that. When the soda is cold, the carbon dioxide is sluggy, and slow, small amount will leave. Then when you open a warm soda, they take off. So the soda gets flat. You got a flat soda because it's warm, and on a sunny day you open that thing there, carbon dioxide begin to run. All right, let's take a look at table 13.2, solubility of carbon dioxide in water. Okay, so when the temperature is 0 degrees C, that table, somebody did a work here, bit of a job here. So we're gonna follow this person just like the previous table we had before. All right. So now we're doing temperature, we're doing pressure, we're doing solubility of gas. And this gas in question is carbon dioxide, not different gases. The same gas. The pressure is the same. The only thing that is changing here, the variable is the temperature. Everything else is the same except for the temperature. All right. So here we go. At 0 degree, at 1 atmosphere, you weigh 0.348 grams of the carbon dioxide, and then you dissolve it in 100 milliliters of water at 0 degree. All right, watch to see how much. You see what happened? You got more carbon dioxide being dissolved at 0 degree. When we up the temperature to 20 degree room temperature, the same pressure, you see that? We couldn't dissolve 0.348 anymore. We can only dissolve 0.176 grams because the carbon dioxide just keep going, keep skipping. All right, so we have managed to dissolve 0.176 grams. When we double the temperature from 20 degrees, we got 40. The same pressure. Look at that. Oh, we have a problem here. We're struggling now. We're struggling to keep the carbon dioxide in our 100 milliliter of water. Look how much we got. We got 0.097 grams in there. That's all we got. When we add 20 more to the 40 degree, we got 60 degrees Celsius. Pressure is the same. Oh, look at that. It's the most struggle. The struggle is greater because now we can manage to get what? 0.058 grams of the carbon dioxide in the 100 milliliter of water. You see that? So this person sat down to do the experiment. Jelly, I'm asking you to go and do the experiment when this course is over. Make a nice table. All right. So pressure also influences the solubility of gases. We just dealt with temperature. Pressure was the same in the past experiment. Now we change the system. Temperature going to be the same. Pressure will change. And see what happened. How much carbon dioxide can we dissolve? So we see, according to Henry's law, what did Henry say? The solubility of a gas is directly proportional to the partial pressure of the gas above the liquid. Now, here, partial pressure, we're talking about Dalton way back then. Partial pressure. Partial pressure simply means that you have several gases in a given environment. Each of them is holding on to its own pressure. So we can add the pressure according to Dalton to get a total pressure. So the partial pressure, according to Henry's law, it says that if we double the partial pressure of a gas, we double the solubility. The partial pressure of a gas will double the solubility. So let's take a look. When the temperature is 0 degree, 1 atmosphere, it will be the same like we had before, 0.348 grams. That won't change from the last table we did. Okay. So So this is the table we just that way will be the same. All right. So same temperature. When we double the pressure, look at the so we have managed to put in more carbon dioxide in 100 milliliter because we pressurize the carbon dioxide, so it's there. When we increase the atmosphere pressure again, look at that. Yeah, so therefore, if you drink a soda that has 0.348 carbon dioxide in it, compared to someone who drinks 0.69, they begin to feel it in their throat. If you drink a soda that has 1.044, oh my goodness, your throat, it'll be so much in your throat. All right. So that's the difference. You can tell who put how much carbon dioxide. And so when you open it up, you hear a loud sound because of that pressure that is being on up. All right. So we can calculate the solubility of the gas at a new pressure using Henry's law. So how do we use Henry's law? We have a solubility, all right? So the new pressure that we want, we'll express that new pressure over the old pressure that we had to give us a new solubility, all right? With a new solubility. What is the solubility of oxygen gas at 25 degrees C and the partial pressure of 1150 torr? If the solubility of the oxygen is this. This is a solubility. And solubility is what? Gram per 100 milliliter of a liquid. Okay? All right. So, and we have a pressure of 760. That's the old pressure. So this is the pressure we want. We want this, 1150 torr. That's our goal, to have that. So we start with it. We start with the solubility at hand. The solubility at hand is based on 760 torr. But we need a new solubility. All right, new solubility. So to have a new solubility, we got to have a new pressure. Gotta have a new pressure. So the bigger the pressure, the bigger the solubility. You see that? So therefore, we're dissolving more stuff. We got bigger pressure. So this is what Henry was doing. So therefore, it's named after him, Henry's law. So if you have take for instance, let's go back. Okay, here we go. This is the solubility here. This is the solubility here, 0.3. Okay, now if we want this solubility, the new one, which is 0.696, we gotta do what? We gotta find a new pressure because the old pressure was 1 atmosphere. So the 2 over 1 atmosphere, times this solubility here will give it a new solubility. We can use Henry's law. So the table here also displays Henry's law. So keep that in mind. All right. So we say, okay, there are some people that like strong carbon dioxide in their throat, in a soda. So now we're going to investigate what pressure should we give to these people. Let's find a pressure. All right. So this is what Henry's law is all about. So you got a solubility. All right. So you need a new solubility. All right. So therefore, you ought to have a new solubility. The new solubility can go with new pressure. So you express the new pressure over the old pressure times the old solubility to give it a new solubility. It's not that difficult. You can do that experiment. All right. when the two liquids make a solution, the solute is the lesser quantity, which we mentioned earlier, and the solvent is a greater quantity. Okay, so recall, remember that recall? Take you back to the net dipole. Dipole, when we're doing the intermolecular forces, we'll talk about those, the hydrogen bonding, the dipole, the London dispersion forces. Now, this thing still following you. They'll follow you big time in solution making. So recall, that a net dipole is present in a polar molecule. We talk about polarity. Polarity, we have a covalent bonding, and one species is more electronegative. Electronegativity, we talked about that yesterday, is pulling the electron to itself, creating partial pole, negative pole. That's the stuff we talked about yesterday. So yesterday will be a prerequisite for this particular session. So that is a big time in solution making. Now let me tell you my solution story. There's a guy, if you know how to make solution for research, you make a lot of money. Because in a research, if the solution is great, everything will be great. Right now, we're talking about this virus is trying to make vaccines and all that kind of stuff. This is a solution making time. So this guy was so good at making solutions. And when he comes in the morning on his job, you would take this alcohol and making his alcohol solution, and you would drink that. And you would get so drunk, you could hardly stand up. But he was good at making solutions. So the company wanted to get rid of him. They wanted to get rid of him, but they couldn't find anybody that could make solution as this guy. So they figured out, what can we do? So what they did, they took benzene and put benzene into the alcohol and wrote on the wall, alcohol is denatured, drink it at your own risk. He came in one morning, he looked on the wall, he noticed that there was benzene in the alcohol, so he couldn't drink that anymore. Oh, the company saved himself. Plus, he didn't get fired. He kept his job, but he couldn't drink the alcohol anymore, and he could still do his work. Somebody came up with an idea. So solution making is a great place to be. If you know how to make solution in research, you'll make a lot of money. So recall that a net dipole is present in a polar molecule. Water is a polar molecule, we said that, right? The covalent bond between the oxygen and the hydrogen. Oxygen is more electronegative compared to the hydrogen, so therefore it pulls the electron to itself. Look at the structure of water. We talked about structure of water yesterday. You got a delta negative, meaning electrons are going there. Delta positive electrons are coming from there, being pulled from there. So that is a dipole. That is a dipole. So look at the other side of the water molecule. There's also dipole. So therefore, that is a net dipole. All right, net is net dipole. So that net dipole, look at the structure on the right-hand side. This is how we write. So they equal. So therefore you have net dipole with the arrow going up there. Net dipole. So we say like dissolve like. A polar solvent will dissolve polar solvent and ionic material. All right. So you got to know that about making solution. Okay. Now, so a liquid composed of polar molecules is a polar solvent. If the solvent is something that is in large quantity, that is going to do what? Do the dissolving. So therefore, if that solvent is polar, like water is a polar solvent. So a liquid composed of nonpolar molecule is nonpolar solvent. So You cannot take non-polar material and put it into a polar material. It's not going to work. All right. There'll be a line of demarcation. Take a look at hexene. Hexene is non-polar. Water is polar.
Excuse me, Professor.
Uh-huh.
So pretty much you have to always keep the polar with the polar and the non-polar with the non-polar.
Very good. Let's celebrate that. Celebrate. That's right. Okay. Polar with polar, non-polar with non-polar. That's how it goes. There'll be no line of demarcation. So hexene is a non-polar solvent. So when you put hexene in water, and it's lighter than water, density-wise, it will float on water. You can see the separation. But when you take alcohol and put alcohol, low carbon alcohol in water, you're not going to find out, like ethanol, that rubbing alcohol. You put it in water, you're not going to see any line because alcohol is a polar solvent. So it's water. So therefore we see, take a look at the table. Let's look at the table. Table 13.3 selected polar and non-polar solvents. Polar solvents. Water is a polar solvent, and hexene is a non-polar solvent. You can't see eye to eye. Methanol, which is a 1-carbon alcohol, is a polar solvent, and heptene is a non-polar solvent. Ethanol, 2-carbon alcohol, is a polar solvent. Acetone. Now, ladies, when you go to the nail shop, that cool stuff that they use on your nail, that's acetone. It is a polar solvent. So next time you go to the nail shop, now you can now look at it, say, hey, I see. That's what the professor was talking about. Acetone is cold. I know many of you have experienced it. You've been to the nail shop, practically all of you. All right. So methyl ethyl ketone is a polar solvent. Formic acid is a polar solvent. Acetic acid is a polar solvent. Now come on, also hexene, nonpolar, heptene, nonpolar, toluene, nonpolar, carbon tetrachloride, nonpolar, chloroform, nonpolar, methylene chloride, nonpolar, ether ether, nonpolar. So as a solution making person, you got to know your polarity. You got to know what goes into what. All right. So polar solvent dissolve in one another. So polar solvent will dissolve in one another. Non-polar solvent will dissolve in one another. This is what we call like dissolves like rule. Like dissolve like rule. Methanol dissolves in water. But hexene does not dissolve in water. Hexene dissolves in toluene, but water does not dissolve in toluene. Simple as that. Like dissolve like. So you gotta know what's polar, what's not polar before you even start your work. Now, take a look at two liquids that are completely dissolved in each other are miscible liquids. They're called miscible liquids. Completely dissolved in each other. All right, two liquids that are non-miscible in each other are immiscible liquids. Polar water and non-polar oil are immiscible. You take oil and put it in water. Look at that. You see, water is a network. I told you, not just one water molecule. You see the dotted lines? That's a hydrogen bonding going on between water molecule. All right. So we talk about the water molecule is a dipole, and it also, it has hydrogen bonding, and also we said that all molecules have London dispersion forces. All right, those are intermolecular forces we talked about before. So polar water and non-polar oil are immiscible liquids and do not mix to form a solution. So you cannot have a solution. From the beginning, we define solution to be homogeneous. So that is not homogeneous. That is a heterogeneous. as long as you can see separation, division, that is heterogeneity. All right. So that is it. That is not a solution. Keep that in mind. When a solid substance dissolves in a liquid, the solid particles are attracted to the solvent particles. When a solid substance, let's take sodium chloride for instance, dissolves in water, the solid particles are attracted to the solvent particles. All right? So sodium chloride is an ionic substance. Water is a polar solvent. So polar solvent will dissolve ionic substances. So in solution, you have sodium ion and chloride ion. And so so the water molecules surround each of these ions in solution. All right. So what happened is when the water molecules surround the sodium ion, the oxygen will turn to the sodium ion. You got oxygen is negative, partially negative, and the sodium ion is positive. The chlorine ion, the hydrogen will turn its face and face the chlorine because hydrogen is partial positive, and so therefore they will line up with the chlorine, which is negative. That's what happens in solution. That's what I mean by when a solid substance dissolves in a liquid, the solid particles are attracted to the solvent particle. When a solution forms, the solid particles are more strongly attracted to the solvent particles than to each other. All right? So you got A, B in solution. All right? And the separation of charge takes place. We can also predict whether a solid will dissolve in a liquid by applying the like dissolve like rule. So you have a solid. That's solid that you're not familiar with. So you say, okay, I'll find out whether this solid here will go with the polar solvent or will go with your non-polar solvent. So you bring out your polar solvent, you bring out your non-polar solvent, and you take some of the solid, same amount of solid, put it in each one, and stir it up and see what happens. So if this solid can be dissolved in the polar solvent, it will go into solution. Whereas if it cannot be dissolved in the polar solvent, dissolved in non-polar solvent, it would do it likewise. So that like dissolve like rule will be applied right there. So ionic compound like sodium chloride are soluble in polar solvents and insoluble in non-polar solvent. So you take some salt and put salt in hexene, nothing's gonna happen. Or toluene, that list, the table that we just saw, you know, you have that table on your wall somewhere. You can look at it and see which is polar, which is non-polar, and make that determination. Polar compound like table sugar, cane sugar. All right? Soluble in polar solvents and insoluble in non-polar solvents. All right? So that's why when you take sugar and put it in water, it goes into solution. Non-polar compounds, the naphthalene, mothball. Are you probably familiar? It smells real nice. Mothball called naphthalene. All right? Are soluble in non-polar solvents. The naphthalene themselves are non-polar, insoluble in polar solvents. All right. So, why is the beam of light not visible in a solution? This is a very powerful area we're going to be discussing now. We're going to be talking about colloid. Colloid is so powerful. There's a lot of money people are making in colloid. So, solution, if you know how to make solution, there's a lot of money can be made in solution. So some companies spend their time preparing colloid colloidal solution. All right. So here's an example. The solution. So we said, okay, we said solution was homogeneous, right? Homogeneous, and no particle exists. All right. So the solution at the right of this slide is a colloid. So you see the two containers there? We shine a light through the two of them. The first one, the light didn't shine through that solution. The second one, because there are particles in that solution, in this one here, the one to the extreme right. So there are very tiny particles in there called colloid. So that's a colloidal solution there. So a colloid is a solution with large particles. All right. The homogeneous solution has no particles in it. So the light will not participate inside that solution. But look at that. Look at a colloid solution. All right. And every solution is good for something. All right. There's another one called suspension. Suspension. So we got solution. We got homogeneous solution. We got a colloidal solution, and we got suspension. So look at the particle size. The particle size range from 1 to 100 nanometers to be a colloid. Anything above that is a suspension. So the particle size for colloidal solution gotta be 1 to 100 nanometer, and it can exhibit that the shine of light in that solution. All right, the solute particles in a colloid are large enough to scatter the light. So you see how it scatters light? Scatter the light via a phenomenon known as Tyndall effect. All right, so you see that. So this is one way you can tell whether a solution is a homogeneous solution or colloid. All right, now, when a soluble crystal is placed in a solvent, it begins to dissolve. The solvent got fingernails, begin to squash at the crystal. It starts using fingernails. The solvent got fingernails. All right. When the sugar crystal is placed in the water molecules attack the crystal. The water molecule got some fingernails and began pulling away the solute. Pulling away the solute. You see that? You see how the water molecules surround that crystal there? Pulling away the solute. All right? Now, this is what we call the sugar molecule held within the cluster of the water molecule called a solvent cage. So they form a cage around the crystal, pulling them, just pulling it into the solution. All right, that's called solvent cage. So the solvent cage, the solute. When a sodium chloride crystal is placed in the water molecule attack the edge of the crystal. In ionic compound, the water molecule pull away positive and negative ions. The anions are surrounded by the positively charged hydrogen atom, as I explained to you earlier. The negative ions are called the anions. So because the hydrogen ions are partial positive, so there's an orientation. The water molecule just oriented itself. The hydrogen will phase the anion, and the cation will be phased by the oxygen. Take a look at that. Dissolved sodium ion. Look at the sodium ion. You see the oxygen in that picture there, facing the oxygen from the water, facing the sodium ion there. And take a look at the chlorine ion. You see the hydrogen now in the water molecule facing that. That's what I was trying to explain to you earlier. This is what happened in solution. All right. So there's the anions and cation. Okay, that's what happened. All right. Now, there are three ways we can speed up the rate of dissolving for a solid compound. So you got this crystal in solution, you wanted to speed it up. So you want it to dissolve faster. What do? You can heat the solution up, it will dissolve faster. This increases the kinetic energy. You know, we talk about there are two kinds of energy, potential energy, kinetic energy, way back then. And so kinetic energy is KE, you got 1 mv squared, actually is G. Increase energy and it moving faster. And the solute is attacked faster by the solvent molecule. So the thing will work real fast, scraping the thing into solution. That's one way. If you want to hasten the solution making. All right. If you have stirring, you can stir. So you can stir the solution. This is increase the interaction between the water molecule and the solute. The interaction that we just saw. You see that the interaction between the oxygen and the sodium ion, chlorine. So that interaction can be increased by stirring. All right? Increase the interaction between the water molecules and the solute. Now, if you have a grinder, you're going to increase the surface area. If you have a grinder, you can grind the solute. Grind it real well. Before you put in the solvent, attack. So those are the three areas. If you're in a solution making business, those are three areas you want to consider. Okay, depending on which one is up to you as a solution maker. Any questions so far? Okay. So now we're gonna see all this graphically. Graphs, we say graphs are so important in sciences. We can go on a graph and pull information off the graph. It's faster. Okay. So solubility, we talk about solubility, mass for 100 milliliter of a solvent. The mass of solute per 100 milliliter of solvent. That's the solubility we talk about all day long. The solubility of a compound is the maximum amount of solute that can dissolve in 100 grams of water at a given temperature. Now we say the water, we use 100 milliliter, right? Okay. Well, we can change that, volume times density. The density of water is just 1 gram over milliliter. So when you multiply the volume, 100 milliliter that we've been talking about all along, by the density of water, you get 100 grams of water at a given temperature. That's how that 100 gram is gotten. So now we can use 100 grams. All right. So this is a mass situation here. So in the general situation, a compound becomes more soluble as the temperature increases. Temperature when you increase the temperature, we just talk about heating. All right, we just passed the 3 methods. We talk about in terms of dissolving, or we say heating was one of those, right? So we increase the temperature. So you have a two-dimensional graph here, solubility versus temperature. Solubility versus temperature. How soluble something is will be based on the temperature in question. So we start from 0, and the scale here is from 0 to 50, 50 to 100, 100 to 150. The scale for the temperature, 0 to 25, 25 to 50, 50 to 75, and 100. All right, so take a look at the sugar line, All right, now when you go to the line where it stopped there, you see that 50 there, between 50 and 75, we know the difference is 25. 1, 2, 3, so 5, 10, 15, 20, 25. So this is 55, this is 60, this is 65, this is 70 to 75. So every move we make is a 5 degree temperature increment. So you see where it's almost 55, 60 for the sugar, way up there, a little bit, it's very close to that. And look at the temperature. Look at the temperature we got from here to 50. So 50, what is it in between? So 10, 20, 30, 40. All right. This is 60, 70, 80, 90, 100. So the space is 10. So we got, so from here to here is 60. This is 70. That's 80. And close there is 90, a little bit above 90. That's the sugar line. Everyone see that? So if I wanted to know at this solubility, okay, how much sugar can I get in at 25 degrees? So I can go from that line and drop the level down to what? To 25. So this is where, so the graph is so important. We can find out the new values of solubility from the graph based on the temperature, okay? And so on. So the graph is very, very important. So in general, a compound becomes more soluble as the temperature. So as you go from 0 going up to 100, you notice that what's happening. You see the sodium chloride line. You see the potassium chloride line. You see the lithium chloride line. Now what happened is, whenever you're doing an experiment, you don't want to have too many variables, okay? So we see that the only big variable here is that sugar. Now, you notice that lithium, potassium, and sodium belong in the same family, okay? So if we use chlorine, if we use chlorine for all of them, you see, we can see the difference between lithium, potassium, and sodium in that family. You got to belong in the same family. As you go down, what happens? As you go down, the atomic number is getting bigger as you go down. So it makes a difference there. All right. So we see that. Look at lithium is way up there, according to that family. Next to, then we see that potassium is right there, and sodium is right there. So we see, okay, the difference there is not the chlorine not a difference, but we can see difference because of the lithium, the potassium, and the sodium. But if we had lithium chloride, potassium carbonate, and sodium nitrate, it is very difficult to tell the difference. So when you're doing research, you gotta make sure you narrow down the variable. Narrow them down, don't have too many variables that you can't tell what's happening. So you got to, the sugar is all by itself. Okay, it's completely different. All right. So this is how when you do research and you find out the difference in something, you want to make sure you narrow down those variables. All right. So we see here a solution containing exactly the maximum amount of solute at a given temperature. This particular solution you refer to as a saturated solution. It has a maximum amount of solute at a given temperature. If you change that temperature, it will not be considered a saturated solution anymore. It's saturated at a specified temperature. So a solution that contains less than the maximum amount of the solute will be considered unsaturated. So these are the things that you got to pay attention to. What makes a solution saturated? Because every time we get to this temperature, everything goes in the solution. All right? And so we see that under certain conditions, it is possible to exceed the maximum solubility of a compound. The solubility is the mass of the solute over the mass of the solvent. 100 gram of the solvent. So we keep it 100, so we will know that everything is based on 100. You can't have 1,000, 100, and 10,000. No, you cannot operate that way. You got to have one thing that is common to everything. You got very few things that are different. So the solution with greater than the maximum amount of solute is a supersaturated solution. So then let's say we have a line. You start with a saturated solution. All right, that's your baseline. So the saturated solution becomes the baseline, and every time we go below that line, we go to unsaturated system. Every time we go above that line, we're into the supersaturated system. See? So you prepare a saturated solution. And then from that saturated solution, you can prepare unsaturated solution and supersaturated solution. Because the saturated solution becomes your baseline. Because it carries the maximum amount of solute at a given temperature. So therefore, that's very, very important. So if I'm going to prepare an unsaturated solution, I will design my saturated solution first. Once I make my saturated solution, then from that saturated solution, I can now make my unsaturated solution. If I'm going to make my supersaturated solution, now I can up the solute so that I can make my supersaturated solution be based on what I want to use it for. If the work I'm doing is calling for unsaturated solution, so I prepare my saturated solution as a standard. Just the other, what do you do? You got prepared yesterday. You did standardization. That is very, very important. Now, let me tell you, when I was a student in college, I was sponsored by Firestone, the Firestone Rubber Company, because my father worked for the rubber company. So they sponsored us, through college. And during the summer period, I used to work at the chemical research. All right. So I did titration. Titration was the first thing that I did when I got into the chemical industry. So I'll prepare my standard. I'll do my standardization like you all day yesterday. All right. You prepare your standard, and that standard they prepare, I can use it for the whole week. That concentration that you got yesterday, you can use it for the whole week, and then at the end of the week, and then you go to test it to see whether the concentration is still whole or is not holding. So you do another standardization. If it's still the same, then you know you got it going. So standardization is very, very important. It lets you know what to expect. So it's the same thing with this saturated solution. So what I used to do, I do my standardization on Friday. And then when I come in Monday morning, I do all my titration all week. Then Friday, I go back and check. Go back and check to see, am I still holding on to my concentration on that? If I'm not holding on to it, then I'll redo it again. I'll create a new standard. That's just standardization, is a precise way of figuring out your concentration. That's very, very precise. If you want to be precise in knowing where your concentration is for a given system, then you need to do standardization that you got that's the purpose of doing standardization. So today, some of you already did the acid base. Now, that number you got yesterday from the concentration you got for the sodium hydroxide yesterday, you could have used that today, in today's experiment, okay? That number you can use again, but if the lab provided you with concentration, then you don't have, but I'm letting you know the purpose of a standardization. So saturated solution is very, very important. Prepare a saturated solution. Go up on it, you're going to be making what? Supersaturated solution. Go down below it, you're making unsaturated solution. So, let's see now. Here's the line I'm talking about. It's a line, graphically, I've been talking about all morning. So at 55 degrees C, the solubility of sodium acetate is 100 grams per 100 grams of water. You see the saturated line of sodium acetate? So I'm gonna be preparing my supersaturated solution of sodium acetate. I want to prepare my unsaturated solution of sodium. So I have the job. This company, you hire, and this is what you do all day long. You come in, you clock in, and you are preparing saturated solution, unsaturated solution. The solutions are very important for what the company is doing. So the first thing you want to do, you want to prepare what? Saturated solution first, because that's the baseline. Based on that, you can prepare the super and the unsuper. Okay? So here you need this temperature to prepare the saturated solution. If you change the temperature, no, you're not going to have saturated solution anymore. So you got to maintain that temperature. So you prepare the solution here. And so now, if a saturated solution at 55 degrees is cool, let's do that now. So we're going to drop down the temperature. It's cool to 20 degrees C. You cool it down to 20 degrees C, coming down, all right? Yes, 55 right there. Go down to 20 degrees C. What's going to happen? You are preparing what? A supersaturated solution. When you decrease the temperature, you are preparing the super, because the particles now begin to they come closer to each other, closer and closer, closer. It's just like when you take a salt solution and put it in the freezer, what happens? You begin to freeze. So now they're coming together. Temperature is low. All right? So that's the same concept, freezing things in the freezer. Supersaturated solutions are unstable. They are not, you cannot rely on them. They're not stable. They are not stable. Keep that in mind. The excess solute can readily be precipitated. So now they form a precipitate. You're familiar with precipitate. Remember with their precipitate? We took clear solution, mixed them, and we started yellow solid, whatever solid, purple solid, whatever solid you got, that is a precipitation. So if you want to design a precipitation going solution for you, then you go with a supersaturated. So from the baseline, you're gonna decrease the temperature. You're gonna decrease the temperature because you're looking for looking for a precipitation from sodium acetate, sodium acetate. All right, so you got that. Now, let's say now you don't need that precipitation. All right, so now, like I just making solution is so important. This class is so important. This class can make you good money. Pay attention to this class. A single crystal of sodium acetate added to the supersaturated solution of sodium acetate in water causes the excess solute to rapidly crystallize. So now the people that the crystal chemists, these guys make crystals all day long. The crystal chemists. So a single crystal of a sodium acetate added to the supersaturated solution. So we made a supersaturated solution here by dropping the temperature to 20 degrees. All right. So when we add a single crystal of the sodium acetate, what happened? What happened is we have excess solute. So we want to make crystals. So people, and the crystal chemists, they can fool you. They can make all kinds of crystals, several crystals. And many are in the crystal market buying crystals all day long. Well, this is what they do. So here we have here. Look at the first beaker. It's clear, right? Now look at the needle formation. All right. Now, a crystal will drop in there. You see that crystal right there? See, that's exactly what they do. So they are very skilled in making crystals. Oh. Let's take a little break. I'll be right back. Okay, so I'm back. So that's very important. Some of you might change your mind and do a lot of things, on the side besides a career. This is it. Now, so let's talk about the mass, something that you're going to be doing from the Pacific Ocean. So this will help you right here. The concentration of a solution tells us how much solute is dissolved in a given quantity of solution. So when you take that water from the Pacific Ocean, you have no idea how much salt is in there. You have no idea. So you're going to weigh the solution, the amount, whatever the volume you got from the ocean, you're going to weigh that and have a number. Then you're going to evaporate the ocean water and you get this salt. Then you weigh the salt, all right? So the weight of the salt divided by the weight of the solution times 100, that is the mass concept we're talking about. That's what you should be doing. After the course is over, go to the Pacific Ocean and do that. I want to hear from you. So the concentration of a solution tells us how much solute is dissolved in a given quantity of solution. So the Pacific Ocean is a solution of salt water. We often hear imprecise terms such as dilute solution or a concentrated solution. There are two precise ways to express the concentration of a solution: mass percent and molarity. Now, what you did yesterday in a lab, that's exactly what you were doing. You did a titration, standardization for precision. You want to be precise, you got to do that titration in order for you to get the exact precision you need for your concentration. You can do it by mass, the mass of the solute divided by the mass of the solution, or the mass of the solute over the volume of the solution, and then change that volume. If it's in milliliter, you take it a liter, because molarity is moles per liter, moles of a liter. All right, these two are two precise ways to express. So this is whether it depending on which company you work for. Next time you go to buy something, look at the bottle, like vinegar or something like that, and it will tell you 2%, 3%, 5%. This is what they do, and you can investigate that. You can find out whether the company is right or wrong. All right, now, so here we go. Mass percent concentration compares the mass of the solute to the mass of the solvent. All right, the mass percent. Now this is going to be on your exam. Concentration is the mass of the solute, so make sure you know this well. Solute dissolved in 100 grams of a solution. So the reason why I say 100 grams of solution, we base things on 100 milliliter of the solution, of the solvent. So now, if the solvent is water, the density of the water is 1. So volume times, concentration will give you that. All right. So the mass of the solute or the mass of the solution times 100. That's mass. That's what they call mass percent. Sometimes students confused with this, they try to divide M into M. No, you can't do that. So this is just mass. Taking one mass divided by another mass. All right. So here we go. How we make solution. This is a solution. Solution is we say solute plus solvent. So look at the denominator. So the mass of the solution, when you hear solution, you know is what? Solute plus solvent. So the mass of the solute, so you add these two together, whatever this is, and that is, will give you the solution. Multiply by 100. Okay. Now, here's an example. Let's see, sometimes the people make an error. I don't see if there's an error, you can catch that error. A student prepares a solution from 5.00 gram sodium chloride. All right? The student go in the lab. Now, they are in the lab, there are three types of balances. We had a decigram balance, centigram balance, and a milligram balance. All right? Deci will be what? 10. Centi will be 100. And milli will be 1,000. Okay? The milligram balance is more accurate compared to the centigram and the decigram. But this number here, 5.00, that's three significant digits, and we had two decimal places. So that is going to be what? The centi. All right, 3 decimal places will be the milli. So they use the weighted salt and dissolve it. Then the water weight now is 7.0 grams. How do you weigh the water? They have taken 97 milliliter in a graduate cylinder. So immediately 97 milliliter of water will translate to 97.0 grams because the density of water is 1 and the density of a gram of a milliliter, and milliliter times gram of milliliter will give you gram. So that's one way you can tell how many grams in water. You don't have to go weigh the water. You don't have to. All right. So therefore, just the volume, multiply the volume by the density, you have to. So they have 97.0 grams of water. What is the concentration in mass? So what do? We look at this. So 5.00 grams of sodium chloride plus a 97.0 gram of that times 100 will give it a mass. The mass of the solute or the mass of the solvent. So if you add those up, if this is added up correctly, and let's see that. Take your calculator, everybody, try this problem, test it. Test this problem. All right, grab your calculator. We got 5 plus 9, 7. That's 102. Okay, the denominator is okay. All right. So we have 5 divided by 102.02. All right. That is 0.0490, right? So move the decimal point, 2 places, two places, and you have 4.90. How many got that? Did you try?
I got that, Professor.
Very good. Good for you. All right. So here's another one now. Masman, we can write, we dealt with unit factors. So we can apply unit factor in this area too.
Oh, wow.
We can write several unit factors based on the concentration. 4.90 mass percent.
Okay. Professor, are these all the different ways you can write the answer?
Exactly. So now you can.
Oh, man.
Tell him that. Tell the professor, stay quiet, you're in class. All right. So whenever when you hear percent, 100 comes to mind. Okay? So you know when they say 4.90 mass percent, so you know the solution has, we don't know, if you don't know how much of this, how much of that, you express the solute over 100 gram of the solution. Okay? Now, so this factor here, if you reciprocate this factor, you get this one. This factor right here is reciprocation of that. So depending on what is given as a starting point, you can determine which factor you're going to be using. Same thing you did when we're doing the unit factor. Okay, same thing. All right, so what mass, let's try this problem. Everybody try this problem. All right, what mass, see if it's correct. What mass of a 5.00 mass percent solution of dextra contain 25.0 grams of dextra? All right. So we want, you see that now, everybody? This is the same thing we learned before. What do we want? What is you know, what are we given? And what factor are we going to use? So look at it. We want grams because it say 1 mass of a 5.00 mass percent solution of dextra contains 25.0 gram of dextra. If you had this on the final examination, for instance, you had this question. All right, so right away you know you can't panic. Because once you understand the concept of a problem, you cannot panic. All right, so therefore, what we're giving what? 25.0 gram of dextra. All right, the unit factor, we know that the factor dealing with here will be the dextra is the solute. Right. And it's, so that's how we take sugar and put it in water. The amount of the solvent. So we just say, so we got 100 gram of solution. So know that everything is we got 100 gram of solution. Yeah, 1,000, 100. The solution 10,000. No, is what? 100%. That way you gotta. All right. Have, so 100 gram of solution. Then you know you gotta go. So therefore, now let's watch this now. Now, take your calculator. Let's test this. Take your calculator, everybody. All right. So 25 times 100 will give you what? 2,500, right? Divided by 5. Ever see that? So the solution is 500 grams of the solution. All right. So how will you figure out the gram of the solvent? Anybody? What will you do? How many grams is the solvent? Is anybody home? How will you determine the amount of solvent required in this solution? We know that here's right here. Take a look. The solute plus the solvent, give you the solution. All right. But in a situation where we do not know that the solvent, we just look at it as 100 grams of the solution. All right. So now what will you do? How do you figure out the mass of the solution? Anybody? You're taking the exam and the time is going on you. So y'all going to sit there, do nothing? Figure out, figure out, figure out, figure out. I'll call you when I grab a flag. Thank you. Okay, so did somebody get it? Oh, I'm deducting.
Can you repeat the question? Sorry.
The question is, how many grams is the solvent? Who said that? Jessica? All right, yes. All right, let's celebrate that. You see that there? You got a solution, right? And you got you have the solute, right? What is the solution equal to? Solvent plus solute. You see that now? Did everybody get what Jessica said? Subtracting the solute from the solution, you get a solvent. Who didn't get it? You got it? Okay. So here we go. So that is the mass aspect of designing a concentration for a solution. So now we're going to move on to the next level, which is the molar concentration. So the molar concentration, or molarity, as it is called, is the number of moles of solute per liter of solution. It is expressed as moles per liter. Moles over liter. That is the molarity. All right? Now, that's what you're going to be doing today. You're going to be finding out, you're doing the unknown. Now, when I say unknown, if you look, you go into the lab, look on the bottle. When you say, what is the unknown number? The unknown number is on the bottle of the unknown. Pay attention, everybody. When you go in the lab, those of you who already had a lab, you already found that out. For those of you that are going to be having a lab this afternoon, the unknown number is on the bottle of the unknown. All right? Okay. Now, somebody was asking me the other day. All right. So we see moles of solute over liters of solution. Molarity is the most commonly used unit of concentration in a lab setting.
You said that at the bottle of the unknown, it contains the molarity?
No. The unknown number.
Okay.
Well, I'm not going to make it easy for you that way.
No, I know.
Okay. So just the unknown number, okay?
Yeah.
All right. So what is the molarity of a solution containing 24.0 grams of sodium hydroxide in 0.100 liter of solution? So they had the volume in liter already, so you don't have too much to do there. So we can also need to convert grams. Whenever you're giving grams, your next move is to go to moles. So you got to find the molar mass for sodium hydroxide. Find the molar mass, and which is 40.00 gram per mole. So we know that the mass over volume. Just like you had the mass over milliliter, you can do the same thing, mass over the volume. Okay, mass over the volume. All right. Times this factor. This factor comes from, this is the molar mass factor. All right. So therefore, the concentration for the sodium hydroxide in molarity is 6.00 molar, 6.00 molar. So that number will go on the bottle. You put that on the bottle. That's the concentration. So when somebody pick up that bottle, they know that the concentration here is 6.00 molar. So if you want a different concentration below this concentration, now you could do a titration if you want to be precise. You can do a titration from this concentration by, instead of doing dilution. The dilution method, which is not too precise, the M1V1, M2V2, that is a dilution method. It's not too precise, but that's a quick way of figuring out. All right. So this is how you do. So now remember that. You weigh the thing. So if this volume was in milliliter, they had to change that to liter because the thing is moles per liter. All right. Any question on that? Everybody, you got it right? So we can do unit factor as well. We can write several unit factors based on the concentration of 6 molar of sodium hydroxide. 6.00 mole over 1 liter. You see? Flip that over, flip these over, and we take the reciprocal depending on what you ask for. Here's the problem. Everybody should get involved in this problem. Typical exam question. Typical. So now, suppose you got a job, or you're looking for a job during the summer, like this time, after you got out of this class, maybe you did get a job from a chemical company. So you get in there, they put you to a test and say, why don't you make us a solution, make us a 0.150 molar K2CrO2. This is potassium dichromate. If you don't know that, the name, potassium dichromate. Make out this solution here. 0.15 they say, this is the concentration we need. Oh, he just stand there and start sweating. Say, how did I make that? You got to walk backward. Walk backward. Okay? Is it how many grams of K2CrO2 07 are in 125.0 milliliter of this? So we want what? What do they want? They want mass. So the mass is K2CrO2 07. We have milliliter of solution. So you start with what's given to you. The solution is 125.0 milliliter, which is made out of solute plus solvent. So this is the concentration right here. The solution, all right, times this. This is the solution here. This is the concentration of the solution. So that's why you have 1,000 milliliter because the solution itself is in milliliter. So we can convert the liter, the molarity, which is moles per liter. All right. So therefore, we change the liter to milliliter, 1,000 milliliter, so that the milliliter solution will cancel milliliter solution. Now you see, 0.150 molar is the concentration of the solution. All right, of the solution. So that's why you got to keep that going like that. Don't confuse yourself. So why do you see milliliter of a solution? Because you took some solute and put it in solvent to make that solution, and that is the concentration of the solution. So therefore, now, so the milliliter of a solution, drop out with milliliter of a solution. Now you in what? Moles of the potassium chromate with 1 gram. So now we're going to find the molar mass of the potassium chromate. 2 potassium. You go on the periodic table. Potassium there. You take the weight. Everybody grab your periodic table. Grab your periodic table and find and tell me how they got 294.2 grams. I want everybody to do that. Try that now, right now. Grab your calculator and find the molar mass for K2Cr2O7. I'll give you 5 minutes to do that. 5 minutes.
Professor?
Yes? You got it?
Yes.
Who's talking?
Christy?
Christy, very good. Anybody else beside Christy got it?
Yes.
You got it?
Yes.
Very good. So that's how we find a molar mass. All right. So now that's that factor. So the more of K2Cr2O7 cancel with that. So now you got what? So in order for you to make this concentration, so if you had a job or company and every day you're using this concentration to do your work, when you run out of the concentration of the solution, you know that you're gonna have to always go and weigh 5.52 grams of K2Cr2O7.
Okay, Professor.
Yeah.
So do you multiply the 125 milliliters and divide it by the 1,000 in order to get the grams?
Yeah. Okay. 125.0 times 0.150, right? Times 294.2. You just multiply across, right?
Okay.
And then divide by the 1,000.
Okay.
You got it now?
Yes, I do. Thank you.
Yeah. So if you work in the lab and you're using this concentration, potassium dichromate concentration, and you run out of the concentration for this solution, all you need to do is go to the stock room. You guys are familiar with the stock room. Go to the stock room, look on the shelf, find K2Cr2O7, and go to the balance and weigh 5.52 grams of that. Once you find that, you're going to be working your way towards 0.150. You're going to change that into mole. And once you find a number of mole, you know that you got 125.0 ml that you use every time you do this. Then you express that number of mole over that value, change that value into liters, and you go back, you made a 0.150 molar. So you got to know back and forth, how to make this, when you run it out, and how did you get to this point? It's so important. So that's how we do the molarity in the lab setting. All right. Now, molar concentration. Now this time they're asking for volume now. one volume of 12.0 molar, they give you the concentration, contains 9.51 gram of HCl solute. They give you the molar mass for the HCl. We want volume. All right, so you start with the mass. All right, so they give you the molar mass is right there, and the concentration of the solution. So a 12.0 mole HCl per 1,000 milliliter of a solution. Every time you see solution, think about there gotta be a solute and a solvent. Let that bell ring in your mind. When I see solution, solvent plus solute. That's one of the reasons why the concentration is expressed in solution. Because you took something and put it in something and made something. So keep that in mind. So now, the volume is 20.9 milliliter of a solution. Because you still got a solute and a solvent. All right? So if you know this, you can find out what they are. You got a solution now. We just solve a similar problem. You subtract the solute from there, you know the value of the solvent. All right. Let's do some critical thinking this morning. Take a look at all those things that you got in your house and you never even pay attention to. Many of you got these things in the house, but you walk past them all the time. Cities often add fluoride. Now you know why they add fluoride to drinking water. The tooth enamel is made mostly of mineral, all right? So that fluoride prevents tooth decay by converting some of the, mineral into more resistant to acid. Fluoridation, they say fluoridation. So if you live in an area where there's a concentration for the fluorine put in there, it's in milligram per liter. That is this is the amount that is allowable by the state or city. This is anything more than that or less than that, no. So this is what. So if you're working in that area, water treatment area, this is the concentration you deal with every single day. Rather than prepare a solution by dissolving a solid in water, we can prepare a solution by diluting a more concentrated solution. So if you have dissolving the solid in water, that's one thing we'll be talking about. But if you have a solution that is already concentrated, all right, here's an example. Supposing mother do this all the time. I tell you, mothers are powerful people. She goes to the store and she buys the orange juice in concentrate. Now, the mothers are chemists now. They are chemists. She buys orange juice concentrate, apple juice in concentrate. And she has a bunch of kids. So she can't afford to buy the regular apple juice and regular orange juice. So she buys things in concentrate and then dilute them. That's a chemistry mom. The chemistry mom will dilute the apple juice, the orange juice, whatever. And then she got job fair, and the kids are so glad. They're happy. Thanks, mom. Thanks, mom. But she's doing her little chemistry in the kitchen. That's what we call dilution. So when performing dilution, the amount of solute does not change. It does not change. Here's one example. Suppose you're cooking soup and you put a whole lot of salt in the soup, and you taste it and say, "Ooh, it's so salty, so salty." What do we do when we taste it, it's so salty? We add water to the system. Does that remove the salt from the solution? No, the salt is still there, but we just spread the particles away. Oh, now it tastes good. They add more water to the system, but the same soil you put there, the same soil is still there. All right. So performing dilution, the amount of solute does not change. Only the amount of solvent. So you add more solvent there. So therefore, we call that diluting. So equation, here's the equation we use. M1, the M stands for molarity, times V1. So the M1 V1, that is the concentrated, that's the concentrated apple juice, concentrated orange juice. That's the M1 V1. All right, the M2, you're taking it to M2 V2. All right, by adding the solvent. So therefore, to dilute it. So when you dilute it, now you got new concentration. It's M2, and you got the new volume, you got V2. So this is what you do if you have a concentrated system, all right, and you want to work your way from there. Instead of getting the solid and dissolving the solid and go through the process we just talked about, all right? So you got plenty of the concentrated stuff, and you want to use some of that. You go in the stock room and get that. So the M1 and V1 from the stock room. So you take the amount of material from the bottle, and it has a concentration of M1. All right. So now you're going to be adding water to the system. That will increase. That cause the V1 to go up to V2 now. You increase it. So now when you do that, the M1 has changed to M2. So M1 and V1 are the initial molarity and volume, and M2 and V2 are the new molarity and the volume. Just like Mama, she got the orange juice, the apple juice concentrate, and she got a new thing going. All right, here's an example. What volume of the 6.0 molar of sodium hydroxide needs to be diluted to prepare 5.00 liter? So you want a 5.00 liter. So you have a marker there. If 0.010 molar of NaOH is to be made, that is the new concentration, new volume. So that's your M2, and V2. So you're working your way out of. So you got your M1, but you're gonna take the M1, the volume from the M1, and make a new volume. All right. So take a look. We want final volume, and we have a final volume and concentration. M1 times V1 equal to M2 V2. What is M1? That's the concentrated one now. 6.0 molar. So we don't know. You got to solve the problem first before you start pouring stuff. All right? You can't just start pouring so you don't know what it is. How much to get out of the concentrated bar, you don't know. All right. So what you do is you solve the problem for how much you're supposed to get from the concentrated bottle first before you start the process. So we say M1 V1 is equal to M2 V2. So therefore, we substitute the M1 for 6.0, and the V1 is the variable there that we need. So M2 is the new concentrate we need. This one we need 0.10 molar. Here's the volume we need, 5.00 liter. That's what we're trying to make. So now we got all that stuff in. We can draw a simple algebraic expression there. We can divide both sides by 6.0, and we get to solve for V1. So now we're going to get out of the concentrated bottle 0.083 liters. But I'll tell you what, it is so difficult when you look at it and say, okay, 0.083, that's tough to get out of the bottle. So what's the best thing to do? Convert it to a milliliter. It's bigger in your eye. Milliliter give it big eye. So take it a milliliter, then you use a graduate cylinder, you will pull it out, and they will be the same thing. All right. Get the equivalent into milliliter. All right. So, is that clear so far? Let's change that into milliliter. Let's go back. 0.083. Somebody tell me how many milliliter is that? Figure it out. 0.083 liter. All right. So somebody tell me what it is.
83 milliliters.
83 milliliter.
Yeah.
Everybody got that?
Yes.
Who didn't get it? All right. So you see that it's easier to go to the graduate cylinder, especially when a cylinder is graduate to 100 milliliter. So you can easily pull out 83. But don't just stand there and say, I don't know how to pull out 0.83 liter. I don't know how. I don't know how. Somebody help me. So you got to convert that. All right. So in chapter 9, okay, we talk about stoichiometry. Remember that, stoichiometry? We perform more calculations involving chemical equations, stoichiometry problems. So solution also has, solution is one of the richest chapters in the textbook, in the chemistry textbook, because all we do is make a solution all day long. All right, so that's why they couldn't fire the guy, because he knew that solution, he knew how to make solution. He kept his job for 30 years. See, that nobody could do it like he did. We can also apply stoichiometric calculations to solutions. Molarity known, we take it out to moles known, moles unknown, moles mass unknown. So therefore, let's see that. Here's the problem right here. Oh, look at that problem. You see that now? We got to do what? Write a balance equation. Something like that will be on your exam. My. Ooh, somebody say, well, professor, you're killing me. You're killing me, professor. Something just sitting down on your final exam. 1 mass of silver bromide is produced from the reaction of 17.8 milliliter of 0.105 molar of aluminum bromide with excess silver nitrate solution. You hear the word excess? So now we're going to do what? We're going to apply, what are we going to apply? This is all the stuff we learned from chapter 9. So if the equation balance, everybody tell me, is the equation balanced?
Yes.
Is balanced? Okay, what do we want? We want gram of silver bromide. What do we have? We got 17.8 milliliter. All right. So the solution, so 17.8 milliliter of the solution. All right, solution. Okay, so therefore, here's the concentration for the solution. It's 0.105 moles. All right. So the ml of solution, cancel ml of solution. Now you guys are so, it's a blessing that you're doing all these exam on the on Canvas, you know, and there is multiple choice. I don't get multiple choice exam. That's not me, but because of the stuff we're doing, and that's why I'm doing it. But if you were in a real system, these are the kind of problem I'll give you on the examination. You sit there before me and doing this stuff here. All right? And you got scoring so high because you're on that little canvas. That's all right. That's all right. That's your chance. One of these days I will get you. All right. So you multiply by the concentration. Now this factor, 3 moles of silver bromide, 1 mole of Aluminum bromide comes from the balance equation. That's one of the reasons why it's so important to balance the equation. All right. So now we see all these steps, the things that I canceled throughout. So now 1.05 grams of silver bromide is required. Any question on that? This is an exam question, exam problem. Any question on that? All right. Okay. Somebody say, oh, I'm just gonna guess and say A or B or C and keep going. All right. Gas solubility decreases as the temperature increases. Aha. Gas solubility will decrease as the temperature increases. But the gas is trying to run out of there. Gas solubility increases as the pressure increases. That's right. Pressure, you keep it under pressure, no time to run. And you got no time to run. So we're keeping it down. More pressure. All right. When determining whether a substance will be soluble in a given solvent, apply like, dissolve like rule. Polar molecule dissolve in polar solvents. Non-polar molecule dissolve in non-polar. We're talking about all these are all summary now. 3 factors can increase the rate of dissolving. You can heat something, you can stir something, you can grind something. In general, the solubility of a solid increases as the temperature increases. Saturated solution, very important. It's a baseline. You can do supersaturation, you can do unsaturation from a saturated solution. All right. So a mass percent concentration, we talk about that. Mass of the solute or mass of solution. Molarity is a mole of solute over liter of solution. Dilution process from a concentrated system, M1 times V1 equal to M2 V2. You apply the stoichiometric reaction involving solution. Is a molarity as a unit factor to convert between. So that's it for chapter 13. Tomorrow is the last chapter, acid and bases. Any questions so far? All right. So if you don't have any question, for those of you I will see this afternoon, I'll see you. And for those of you I don't have to see this afternoon, I'll see you tomorrow morning. Have a good day.
Thank you. Bye-bye.
Bye-bye.